Welcome to the deep dive. Have you ever really stopped to wonder where true innovation comes from? I mean, is it just lines of code, complex
Or
algorithms?
is it something, much deeper, something maybe happening behind the scenes, rooted right in our own biology?
It's a great question. We focus so much on the tech itself, the software, the hardware.
Right, but what if the real engine, the core of innovation, isn't just the stuff we build, but the human brain that's actually doing the building?
Exactly. And that's what we're diving into today. We're looking at Taxshila Technology, this
Yeah.
really fascinating framework from Shiva Narayan Taxshila Page.
Mm.
And the idea here, it isn't just about software development in the usual sense. It's about seeing the human brain as the actual, well, the motherboard of technological evolution.
That's a powerful analogy. And what's really groundbreaking about this framework is the core idea.
It is.
That every single phase of how technology evolves is deeply, profoundly intertwined with specific brain circuits, the developer's brain circuits.
Okay, so not just abstract thoughts, but actual physical circuits.
Precisely. And it's rooted in these principles called learnography. Think of learnography as like the brain's unique operating system or grammar for how it learns and how it creates technology.
So like the rules the brain follows to encode new stuff.
Exactly. How it systematically writes and rewrites new concepts, new tech skills into its neural pathways.
Okay, so if learnography is the grammar, then technology isn't just built in a text editor. It's actually cognitively and motorically transferred, stored, and formatted right inside our brains.
Yeah, through a very systematic phase-by-phase progression.
So today we're going to explore how all that brain activity, from those first creative sparks, that flash of insight, all the way to that intuitive finesse you see in really elegant technology, how that drives the whole development cycle.
It moves us beyond just looking at innovation as a purely cognitive thing. We're looking at the neurobiological foundation.
It's about seeing the brain not just as an organ that thinks, but as the engine of invention itself, dynamically shaping the tech and also being shaped by the tech it creates.
Absolutely. It's a two-way street.
So if the brain is this dynamic motherboard, then the developers in this model, they're called knowledge transformers.
That's right. It emphasizes their active role in this whole brain-driven process. They're actively molding and transferring insights within their own neural landscape.
And the key mechanism here, you mentioned it's called brain page modulation. What exactly is that?
Yeah, brain page modulation. It's think of it as the brain's dynamic process of reshaping its internal knowledge maps, like these brain pages.
Okay.
So as a developer learns something new or hones a skill, their brain is literally reorganizing, restructuring these maps. It's the physical change happening in the neural networks that's directly tied to the innovation process.
Wow. Okay. And here's where it gets really interesting for me. This model shows how the fundamental bits of technology, things we take for granted, like association, modular design, logic, creativity.
Visual formatting, system integration.
Right. And even that intuitive execution, these don't just happen. They actually emerge from specific interactions between different parts of the brain. Cortex, subcortex.
Exactly. It's a true cerebral symphony, like the framework says. The developer's brain is conducting this incredibly complex orchestra with different sections playing their part at the right time.
It's a pretty amazing insight. It shows how these different brain regions drive the specific cognitive steps, the motor sequences that lead to structured innovation.
Yeah, it moves us beyond just what a developer does to understanding how their brain is actually making it happen.
And this symphony you mentioned, it plays out over 7 distinct phases, right? In Taxshila Technology development.
Yes, 7 phases. Each one corresponds to specialized functions happening in specific brain regions.
So what are they? Can you list them out?
Sure. It starts with a definition phase, then moves to structure, cognitive, innovative, formatting, then the really key Taxshila phase, and it culminates in the intuitive phase.
Okay, 7 phases. To make this really concrete for everyone listening, let's maybe imagine a developer. Let's call her Sarah. She's starting to build a new app, maybe something AI-powered.
Good idea.
We can follow Sarah and see how her brain is like the engine at each step. So let's start with phase 1, the definition phase, the spark of ideas. Where's that happening in Sarah's brain?
Okay, so this first stage, it really kicks off in the prefrontal cortex. That's kind of the brain's CEO, right? Planning, high-level thinking, setting
The
goals.
big picture stuff.
Exactly. That's where Sarah's creative sparks are firing, where she's drafting those initial mental blueprints for her app, but it's not working in isolation.
No.
No, it collaborates really closely with her association cortices. I think of those as like vast libraries holding all her existing knowledge and expertise.
Ah, so pulling in what she already knows about tech definitions, similar projects?
Precisely. It's that blend of fresh creative sparks from the prefrontal cortex and the structured knowledge from the association areas. That's where the initial definitions get curated.
Okay, so you've got the spark, the definition. But that needs a structure to actually become something, right?
Mm.
So how does Sarah's brain go from those raw ideas to an organized plan? That's phase two, the structure phase.
Exactly. Now, different players step up. Her hippocampus and temporal lobes really take the lead here.
The hippocampus, that's memory, right?
Yep. Crucial for long-term memory, but also spatial navigation. So it helps Sarah mentally visualize the app's layout, map out how different modules or features will connect spatially, in a sense.
Okay, like building a mental map of the app.
Kind of, yeah. And her temporal lobes, they're involved in understanding language, semantics, visual memory, so they help her process the meaning of different components and how they relate, recognize object functions within the design.
So together they build the blueprint.
They help her construct what the model calls a structure matrix. It's a detailed mental template of the design modules, the system architecture, and this whole process is guided by something called insular learnography.
Insular learnography.
How's that?
What's that?
It's like the brain's internal compass for building systematic, scalable structures. It helps ensure that the architectural design Sarah's creating is sound, logical, and adaptable right from the start. It's about building that solid foundation.
Makes sense. You need that solid mental framework, which I guess naturally leads us to phase three, the cognitive phase.
Oh, yeah.
This sounds like where the heavy lifting, the logical work happens.
It absolutely is.
Mhm.
This phase is primarily driven by Sarah's parietal lobes.
Parietal lobes. What do they do?
Think of them as the brain's central hub for analytical reasoning, problem-solving, spatial processing, really manipulating things mentally.
Sure.
The posterior part especially helps her mentally juggle data, formulate specific tasks for the app, simulate different scenarios in her mind, test hypotheses about how things will function.
So really working through the logic.
Yes. This phase fuels the logical engine. It lets her build a precise, scalable, cognitive framework for how the app will actually work internally. Lots of spatial temporal coordination needed here.
Right. And that focused problem solving, that logical work, it must sometimes hit roadblocks, right?
Yeah.
Which brings us, I guess, to phase four,
Yeah.
the innovative phase. This is where the real breakthrough thinking comes in.
This is the exciting part. Yeah. This is where creativity and genuine breakthrough problem solving take center stage.
How does Sarah's brain suddenly generate those aha moments, those novel solutions?
Well, it involves a network. An area called the temporoparietal junction, the TPJ, seems to be a key hub. It helps us shift perspectives, connect seemingly unrelated ideas.
Sure.
And it teams up with the prefrontal cortex again for planning the new approach, the anterior cingulate cortex for error detection and focus, and even the basal ganglia, which is involved in learning new procedures and sequences.
This is a real team effort for breakthroughs.
Definitely. This is where Sarah's brain starts doing radical reconfigurations, taking existing knowledge and twisting it, combining it in new ways to create genuinely new functionalities for her app.
That sounds a bit like object-oriented programming, deriving new things from existing classes.
That's a great analogy. The framework actually mentions that it's akin to the derivation aspect of object-oriented programming, but it's happening neurally through iteration, experimentation, refining ideas within her mind.
Okay, so she's had these innovative breakthroughs, but an idea isn't an app yet. How does it become tangible? That must be phase five.
Yeah.
The formatting phase.
Exactly. Phase 5 acts as a crucial bridge. Those conceptual breakthroughs Sarah just had, now they need to be systematically organized into something executable. Functional blueprints, actual modules.
So getting it ready for coding, essentially.
Pretty much. Her occipital lobes are heavily involved now. That's the visual processing center. She needs to see how the code lays out, how the interface looks, schematic representations.
Right.
And this is supported by other areas like the dorsolateral prefrontal cortex for holding information in mind while working on it, the basal ganglia, again, for sequencing the steps, and cerebellar circuits for fine-tuning the details.
So this is where she's really honing in on the specifics. Task formatting, algorithms, mapping the interface.
Yes, all of that, making sure it's consistent, scalable. The framework calls this the final derivation process. In OP terms, preparing those solutions for real-world implementation, making sure every piece fits and functions correctly.
Okay, that makes sense. Then we hit phase 6. This is the one named after the model itself,
Yeah.
the Taxshila phase. Integration and synergy. This sounds really important.
It is. It's pivotal. This stage is all about integrating and synchronizing everything that's been learned and developed so far. All the knowledge, the structures, the logic, the innovations.
How does the brain pull all that together?
Well, Ceres thalamus plays a big role. Think of it like Grand Central Station for the brain. It relays sensory and motor signals, coordinates the information flow between all these different cortical areas we've mentioned, keeps everything in sync.
Okay, the central hub.
Right. And the cortical connections themselves, those pathways linking prefrontal, parietal, temporal cortices, they're crucial for coordinating everything and putting it into context.
Right.
This allows Sarah to fluidly switch between abstract thinking about the concept, the technical design details, and the actual applied mechanics of coding it.
And you mentioned the insular system, too.
Yes, the insula is key here for internal awareness. It helps Sarah detect potential errors, maybe gauge the emotional feel of the user interface, make subtle judgments and decisions, especially when things are uncertain.
So all these parts working together create, what do the outline call it? A deep processing core.
Exactly. It's where all the disparate pieces of knowledge and skills seamlessly intertwine into a functional whole. The app starts feeling coherent.
Right. So everything learned, developed, innovated, it's now harmonized. It's a unified sister in her mind and hopefully in the code, too. Which brings us to the final stage, phase 7, the intuitive phase, mastery and autonomy. This sounds like where the magic really happens, where the technology almost becomes an extension of Sarah's own mind.
It really is the culmination. It's the result of all that deep learning and subconscious integration across the previous phases. The technology, her app, reaches maturity. It starts to embody intuitive design. It aligns well with users, maybe even shows adaptive intelligence.
And neurologically, what's happening here?
Here, the basal ganglia and cerebellum become even more prominent. They're key for unconscious motor planning, procedural learning, automaticity.
So the things Sarah does without thinking, like typing code really fast or instantly knowing a better way to structure something.
Exactly. Those complex coding skills become second nature, almost automatic. And this phase also taps into something the framework calls dark knowledge.
Dark knowledge. Yeah. That sounds a bit mysterious.
It's not mystical. It just refers to that vast unconscious reservoir of experience and patterns that a developer like Sarah builds up over years.
Like tacit knowledge. The stuff you know but can't easily explain.
Precisely. It's like when a really experienced developer just feels that a piece of code is wrong, or that a certain approach is the right one, even before they can fully articulate why. Their brain has processed countless similar situations subconsciously.
So that gut feeling developers get.
Yeah, that dark knowledge guides Sarah now. It helps her create an app that feels natural, maybe even anticipates user behavior, operates with a kind of embedded intelligence that doesn't require constant conscious effort from her.
Wow. So it's not just about the explicit code she wrote. It's about this deep, almost instinctual understanding that emerges from this whole neural journey. It sounds like Sarah has truly achieved mastery.
Exactly. Her brain has literally rewired itself through these phases to embody that expertise.
Okay, so stepping back, what does this all mean for us, for you listening? If we connect this back to the bigger picture, this research, this framework, it really highlights innovation as a holistic brain-driven process, doesn't it?
Absolutely. It's not just a cognitive exercise. It involves these deeply embedded neural systems working together in very specialized ways to organize, process, and execute the transfer of knowledge into technology.
That's the key takeaway then. Understanding these brain circuits, these phases, it could actually help enhance creativity, optimize how we develop tech.
Potentially, yes. It could foster a deeper integration between our own biological intelligence and the machine systems we create.
How so? Like, practically?
Well, for example, if you know the definition phase relies heavily on the prefrontal cortex, maybe you design brainstorming sessions or work environments that specifically support that kind of divergent creative thinking.
Yeah.
Or knowing the intuitive phase depends on the basal ganglia and cerebellum for automaticity, it reinforces that deep mastery doesn't just come from reading books. It requires deliberate, maybe even repetitive practice to automate those skills neurally.
So it gives us clues for how to learn and work smarter.
Exactly. This isn't just abstract theory. It could be a practical blueprint for smarter development, for boosting your own innovation process.
And thinking longer term, the implications. This kind of brain-based model could genuinely improve how we approach innovation, couldn't it?
You could see it transforming education, how we train the next generation of developers, maybe even how research labs or tech teams are structured to optimize their collective cerebral symphony.
It suggests a future where neuroscience and technology development really co-evolve, informing each other.
It's about consciously applying this understanding to design more effective learning, more effective development processes, cultivating those knowledge transformers for the future.
This has been, well, a really fascinating deep dive. It truly shows that incredible synergy between our brain circuits and the technology we create. The mind isn't just using tech.
It really is the motherboard, orchestrating everything from the first spark to the final intuitive polish.
It's quite a testament to the potential packed into our own heads.
It really is. The potential within our neural architecture is pretty astounding when you look at it this way.
So as you, our listener, reflect on all this, here's a final thought to chew on.
Hmm.
Given that our brains seem naturally wired for this kind of cerebral engineering, this complex dance of innovation, how might consciously designing our own learning, our own development processes, inspired by these neural phases, how might that fundamentally change the pace, maybe even the very nature, of future technological breakthroughs?
And perhaps what new brain page modulations, what new potentials for innovation are still waiting to be discovered within your own mind?